Well, welcome everyone to this Aisenstadt lecture on behalf of the CRM, on behalf of the organizing committee. I welcome everyone. This is probably the most packed I've seen this room. This is probably the most packed this room has ever been. That is, of course, due to our speaker, Francis Bach. He received his PhD in computer science at UC Berkeley. As an assistant professor at École des Mines de Paris at Fontainebleau from 2005 to 2007. Since 2007, he's been research faculty at INRIA, also at École Normale Supérieure in Paris. He received the habilitation à diriger des recherches at École Normale Supérieure Cachan in 2009. He won way too many prizes and awards to mention, so I'm focusing on the ones that I like.
The others are so okay.
It's a biased subsample. 2018, he received the Lagrange Prize in Continuous Optimization from the Mathematical Optimization Society. In 2019, the Prix Jean-Jacques Moreau. He has numerous best paper awards, including the Test of Time Award from the International Conference on Machine Learning. He's also done a lot of important service. He's been the president of the board of the International Conference on Machine Learning, and he was co-editor in chief of the Journal of Machine Learning Research from 2018 to 2023. Broadly speaking, his research areas are statistical machine learning with a focus on optimization, sparsity, kernel methods, graph models, and signal processing, where he's considered one of the world leaders, as is backed up by 70,000 citations, at least. He also has a new book, Learning Theory from First Principles. I'm sure he will sign copies of the book after the lecture. And so without further ado, I hand the stage over to you and enjoy.
Okay. So thanks a lot, Tim, for a very generous introduction. I hope I can live up to it. Also, thanks for CRM for welcoming me here and organizing this event. So today, I was asked to give a general talk audience, and I will, if you want, I should say more meat. We don't say more meat anymore in the 2025. If you want like more math, you can come tomorrow. If you want even more math, it would be like a Blackboard talk on Thursday. But today is going to be like a talk on the interface between optimization and machine learning. So for the non-experts, you will see what the field has been doing in the last 20 years or so. And for the experts, and I see many in the room, you may get slightly bored, but I think it's a good time also to reflect on what has been achieved by many people in the field and what we can do to move forward. So to give a bit of context, okay, I will be quick because I'm sure you're well aware of that. So there is more and more data everywhere. And what I mean everywhere, it's not only in social media and for Google and Facebook, it's also in industry and also in all scientific domains, whether it's humanities or bioinformatics. And for all of those domains, you need to process that data first. And a new paradigm is now you want to do like science with data-driven approaches. Okay, so this has led to a lot of hype in the last like 15 years. And if I had given a talk like 10 years ago, I might have said big data instead, and then I would say data science. And there's a sequence of buzzwords that have been like leading the stage. At the moment, we reached like LLMs, okay? But it's more or less of a similar nature, okay? There's data that you want to learn from. All right, so the recent progress, okay, what is that made AI popular is in various perception tasks. And here I've put like three classical ones. One is like machine translation or any type of NLP tasks. And here the key is that all of those advances have been obtained by learning from data. So for translation, you have seen like millions or billions of sentences from French to English or French to Italian here. And then you want to reproduce on a new sentence. Same thing for computer vision. So this is like image generation. Okay, so this is like all the diffusion models that people talk about, and I will give a talk about it tomorrow. And of course, I cannot escape GPT. Okay, this is what people use a lot. So what has made this possible? Okay, clearly not me, but a conjunction of massive data. Okay, we learn from a lot of data. So to do all of that, you don't need like 1,000 observations. You need like billions and more. A lot of computing power and some, of course, some progress. And at the end, what has made this intelligent, okay, in quotes, because this is a word we never used in the community, is a combination of models, algorithms, data, and computing power. Okay, so you need all of that to make it work. And what I will focus on today is on the algorithmic part. Okay, so in all the pipeline to make this possible, I will consider the one line of code that does optimization. Okay, keeping in mind that this is the one I like. Also, it's the one which is important, but if you don't have all the other lines of code, it won't matter so much. Okay, so I'm going to focus on a single problem, but keeping in mind that you need all of that. All right, so now let's get down to a bit more math. So this is, I'm going to use the classical supervised machine learning setup as a general setup for machine learning. There's, of course, like other ways of doing machine learning, but this is going to be the motivation. So I have some data xi, yi. Xi can be an image, okay, can live in a high-dimensional space. X will be my space. Yi will be my label, my output. So think of yi as being a label or being a real number, something which you want to predict. And the way it's going to be done is by building some prediction function, which has two parameters, h of x of theta. X is your input, and this is you want to predict the output, and theta is the parameter which is associated with the model. Okay, so you have always two parameters, and I'm going to assume that I have a d-dimensional parameter rd. So what are the typical prediction functions? So the simple ones first. This is linear predictions. And of course, here it's linearity in the parameters, okay, not in the inputs. So so if you linear the parameter, you have to be of the form theta transpose some phi of x. And phi of x is often called a feature vector. Okay, this is where you put all the expert knowledge that you care about. And until like 10 years ago, this was by far the dominant or the leading framework in machine learning. And for advertising, for example, phi of x is simply a vectors of 0 and 1s, and the data are you and your navigation history. And for each of you, phi of x will be like one value for each website in the web, and 1 if you've been there, and 0 otherwise. And advertising up to maybe 5 years ago was really doing a big linear model. Okay, so why it was powerful? Because D was very large. So we have put 10 to the 9, but probably this is more like 12 or more at the moment. And but the key, this was a linear model in the parameters. So you're probably well aware now that there are also nonlinear models that are being used, and this is now the state of the art for various tasks. And all the ones I've presented earlier, like vision and NLP, are not based on linear models anymore. And this is the simplest example of a neural network. So this is the task is you have dogs and cats. Okay, X is an image, Y is a label, +1 if you're a cat, and -1 if you're a dog. And the model now has some linear parts, okay, but also some strong non-linear parts. I'm going to start from X. I apply a linear map, theta1, and then I take a non-linear activation function, sigma, okay, component-wise, and then I iterate. Okay, so this is the simple multi-layer neural network. This is, of course, not what is used in the big applications I was mentioning. It's much more complicated. Okay, I will come back to that, but you have like attention layers, you have like convolutions, you have a lot of things. Okay, but what is important for me today is the fact that this is nonlinear in the parameters. It's linear in theta, the last layer, but it's nonlinear in the inner layers. Okay, we will see immediately that this creates a problem. So now I've described like the prediction function. Okay, so two classical ones, linear ones and nonlinear ones. And then the way it is learned, so you estimate theta by framing this as an optimization problem. So this is not really, it has been around for many years. So you build an objective function, which is a sum of some data fitting term and some regularizer. So the data fitting term will be a loss, the average of your data of a loss, okay, between your label yi, this is what you want to predict, and your prediction h of xi theta. And the loss, okay, will be adapted to the type of labels. So if you wish, you can take the loss as being least squares. Okay, so if you have a real valued random variable, or you can take the loss being like the logistic loss. So if yi takes value -1 and 1, then this is a classical loss for binary classification. What I want you to focus on is on the convexity of the loss in H. Okay, so even in most of the deepest networks, okay, the loss here, L will be typically convex in H. Okay, so this is important because when we have a linear model, it's going to be convex in theta, but it's going to be also important when we want to do a bit of theory on the neural networks. Okay, so the loss is convex in H, and we add some regularizer to avoid overfitting. So the idea is that optimization here is just a mean to an end. Okay, we don't care to do well on the observed data. We need to do well on the unseen data. Okay, so it's not the topic of today. Okay, but typically, what you really care about is the so-called test error, which is the error on unseen data. But this is where you need to put some assumptions. Okay, some statistical assumption to relate the testing data to the input training data, and typically you put some independence of the training data with the same distribution as the testing data, classical ID assumption. Okay, today I'm not going to focus so much on that test error business, but this is very important, of course. If you do well here, you want to do well there, and one way is to add some regularizer, but it's not a topic for another talk. All right, so what is convex? Okay, so you have a convex optimization problem. So sufficient condition is that the loss is convex, so this will always be the case today, and the predictions are linear in the parameters theta. So this is an example of a convex problem. Okay, so I'm going to show this several times today. I have a problem in 2D. Okay, d equals 2. The idea being that this is to represent like large d, but d equal 2 is the only one I can represent easily on the slides. And you have it's convex, so this means the level sets are convex, and typically you start from there. You want to obtain the minimizer over there. Okay. All right. So what is the consequences of convexity? Essentially, any reasonable algorithm that is local, that we look at local information, the gradient will end up converging. Okay, and this allows us to get quantitative guarantees. Okay, this is quite important, and this has kept us busy in the last 20 years. Okay, so pick your own subject. Okay, so here there was not enough space to highlight all the benefits of convexity in machine learning and statistics. Okay, but I've put the ones I care about. So this started in machine learning with supervised vector machines. Okay, which is a case where L is a non-smooth function, but it's still like a convex function. Then there were the sparsity years. Okay, where you had a regularizer which is a bit more complex. It's not differentiable, but then there's all those techniques to solve the lasso problem, which corresponds to least squares plus L1 norm. Then there is all the optimal transport setup. There is what I will focus on today on SGD, stochastic gradient techniques for online learning, but there are many others. Okay, and randomized linear algebra is essentially one of them, and this is something which is still very active. So I put only 2020. It's not because COVID killed it. It's because there's less action, but there is more non-convex now. Okay, which is taking some space. All right, give me some examples from research which I'm very familiar with, which is large-scale learning. So what is large in that setup for me will be n will be quite large. Okay, so n will be a big power of 10. Okay, and the dimension of theta can be also quite large. All right, so so what makes the problem very special compared to generic optimization problems is the fact that what we want to minimize is a finite sum or a finite average. So our objective function g of theta is an average of functions. Okay, and fi here is just the loss for a single pair of observation xi, yi plus regularizer. So here I'm simplifying a lot because typically you put not one but mini batch of observations. But at the end, it's the same. You get a finite sum. Okay, so whenever you use optimization techniques, you want to take into account this finite sum structure. And it's fair to say that this was ignored for several years in machine learning. It was forgotten for several years that you should use that finite sum structure. And if you just ignore that finite sum, you just take the simplest algorithm like gradient descent that dates back from a while back, and you so this is an iterative algorithm that you start at some time 0, okay, and then you iterate that equation, which you go along the negative gradient with some step size gamma, okay. And so here the gradient is a steepest descent direction orthogonal to the level sets, and you make one step and then you iterate, okay. As you can see here on my simple convex problem, it goes quite fast towards the vicinity of the minimum, and then it oscillates towards the global minimum, okay. So this is all nice, and I will show like what you can show about that algorithm, but the issue here is that at every time step, okay, to make that big move, you need to compute the full gradient of G, which is the average of the gradients of all local functions. Okay, so if n is your data set, if n is very large, going through your data set will take you forever. Okay, making one move will take you a lot of time. And this is where the stochastic gradient descent comes in. Okay, so this dates back from Robbins-Monroe in the 50s. And the idea is not to take all gradients at every iteration, but just a single one. Okay, and there are various ways of doing it. But to make the math simple, we're going to assume we take a random I of t, a random sample with replacement at every iteration. So this means that if I take the expectation over I of t, okay, I get back the full gradient. Okay, so this is a principle behind it. What is kind of amazing is that it is unbiased. It has a correct expectation, but the variance will not go to 0. Okay, so this is you always make mistakes. Okay, if I were to use a non-random perturbation on the gradient, if I don't set that perturbation to 0, I may not converge. But here, I will converge if I'm allowing the step size to get smaller. So this is like on the same problem, LGD. So first you see that the D term, it's not a descent technique. Okay, sometimes you go up, like the first iteration. Sometimes you go down, but on average you tend to go down. Okay, so this is like the so it may look from the figure that this is inefficient because you do like many more steps to get there, but each of the steps is n times faster than before. So if n is 1 billion, you get strong gains. All right, so what this is like from the 50s, and there is like a lot of improvement. Let me jump back to the work, in fact, which I did with Nicolas Leroux. So if he's on Zoom, hello, Nicolas. And also work which I did with Simon Lacoste-Julien. If Simon is around, bonjour Simon. Not sure. And the idea is to trying to okay. Okay, we can see the chat. Very good. Thanks, Nicolas. And so the idea is not the way we framed it with Nicolas Leroux and Mark Schmidt, but this is the way we framed it with Aaron DeFazio and Simon Lacoste-Julien, using work by Johnson and Zheng and colleagues, was to look at the HGD equation, okay, which is like, again, you go down the one random gradient, and here, if you take the expectation over I of t, you get the full gradient, but as I've mentioned, you get a big variance, okay? So what you can use is a way to reduce variance, okay, which is called variance reduction, which has been around like in Monte Carlo for quite a while, and this can be adapted here. And the way it's going to be done, and I will not spend too much time, is to use path gradients. So here, what is yit will be the gradient of the function I last time, the gradient of function I which I store in my memory at time t. Okay, as I go along, I sample a new gradient. Okay, I'm going to replace my stored value. Okay, as I go along. So every time step, I access a new gradient. I replace my memory. Okay, and then I add those terms. Okay, which is the average of my stored gradient before the iteration minus the stochastic gradient. So you can check that the expectation with respect to the new randomness I of t. Okay, here you get the full gradient. Here you get exactly this. Okay, so the expectation remains the full gradient. So it turns out to be unbiased, and the beauty of it is that it will reduce variance. Okay, and what you can show is that the variance reduction will essentially be at the same speed as you convert toward the global optimum, and you get improvements which can be seen in 2D. Okay, it's still like randomized. Okay, you can still go up, but on average you get you get like quicker with much less oscillations. Again, this is a O of n per iteration. There is some storage, but there's ways of not being impacted by that, which I will not mention. So now this is all convex. So again, this is for convex functions. Okay, so this is where I'm going to show some results. So I'm going to assume that I have some convex objective with some condition number kappa. So kappa will be the ratio of the largest eigenvalue of the Hessians over the smallest eigenvalue of the Hessians. Okay, kappa is bigger than 1. And the image you should have, kappa will tell you if the level sets are more like balls or more like big ellipses. So small kappa, easy, large kappa, difficult. And typically for machine learning, the kappa will come often from the regularizer. And that kappa typically is O of n. So problems that we solve in machine learning tend to be difficult in terms of optimization. They have a large condition number. And what you can show for gradient descent, and those are bounds which are just bound up to constant factors. Okay, this is not like this big O is explicit. You can show that to reach precision epsilon, the dependence in a log of 1 over epsilon. This highlights like exponential convergence. Okay, but the number of individual access to gradients will be n times kappa. Okay, why? Because you need kappa iterations of gradient descent, and each of them costs you n gradients. So you get n kappa. If kappa is n, this is quite large. AGD is the opposite behavior. You lose the exponential convergence. Okay, this is the oscillations that we have seen earlier. But every iteration accesses one gradient, kappa. Then with the new variance reduced techniques, which we have worked on, and we is like my colleagues and me, but also many other people in the community, you replace n times kappa by n plus kappa. So when kappa is of order n, you get a factor of n improvement. Okay, so this is the type of result which you can show. Those are quantitative. Okay, it depends on constant which you can compute. Okay, so in a sense, the goal is to reach the same level of stability as linear algebra. Okay, and we are not totally there yet, but we are approaching it with very precise bounds. And the good thing is that it matches reasonably what you could see in practice. All right, so this is like on the left, the wishful thinking plot. Okay, so if you take the bound which I've mentioned, this is what you will obtain. Okay, so it's a semi-log plot. So time in the x-axis, performance in logarithmic scale. So a line means like a linear convergence. Okay, and what you see that deterministic full gradient will be a line that goes down, but it's quite not very steep. Stochastic gradient will start very fast because as soon as you see one observation, you start to make progress. But then you see like the logarithmic decay, and this is the new algorithm, okay, which preserves linear convergence, exponential convergence, but at a much bigger rate. So this is just like wishful thinking or the plot of the bound. This is what you observe. Okay, so you see various like lines which are like deterministic at the descent, which is a line. Okay, linear convergence, but quite slow. AGD in blue and green, starting fast and then like leveling off, and the new technique. Okay, and this plot has been reproduced many times. So here, the good thing is that you make some predictions, you make some bounds, and then it does match reasonably well. Even better, you can start to make the improvements on the algorithm. When you look at your proof, and we have experts in the room here, then you can start to do, maybe I can sample non-uniformly to make some progress. This can be done. You can accelerate, okay, showing that you can improve over condition number by getting the square root of condition number. You can have like upper and lower bounds. You can show that for that type of problem, am I optimal or not? So you can do a lot of things. Okay, and to me, this is a big success of the whole community that for convex problem, for finite sums, we start to have a reasonably good understanding of practice. Okay, so this is like the positive part of the talk, but I think problem will be now, what about deep learning? Okay, so essentially, for deep learning, for nonlinear models, essentially all of that will go away. Okay, doesn't mean we cannot say anything, but keep this in mind that this is really the we wish we could do that, but we cannot do this at the moment, and I don't think we'll be able to do that anytime soon anyway. All right, so let's go to deep learning. So here I'm going to focus on a very narrow set of models, and I'm going to make it even narrower in the one slide. So like just feed-forward multi-layer neural network, no ResNet, no transformers, no Mamba, no whatever you want to use. Okay, very simple feed-forward. So here there's like 2 hidden layers. Okay, and so here there are 2 questions, and I'm going to tackle only one of them. It's non-convex. Why is it non-convex? Because I have the activation function which is over there. First problem. Second problem, we're going to have a lot of parameters. So the new regime under which those techniques are being used is with like not 6 neurons, but more like millions of neurons. So this is often called over-parameterized. You have many more parameters than you have dimensions, and you can fit the data perfectly. Okay, so typically this should be a warning sign in terms of statistics. Okay, so 2 problems: how do you optimize, and how do you generalize in this over-parameterized regime? So I won't talk too much about it, but what I find kind of a bit surprising is that this over-parameterization will be a blessing for the first one. Okay, what we'll show like, for the next 10 minutes is that being over-parameterized will enable us to partially solve this like local minima issue. So what do I mean by local minima? So this is like a classical profile, same thing in 2D, but since I took it from Lee et al., there is a 3D plot, okay? And this is like a true profile of a neural network training, okay? If you look before, the one which I had before, this one, in fact, was essentially a logistic regression, okay? So this was very simple, okay? A unique global minimum. So what you have in practice is a lot of problems, okay? So you have local minima, okay, all over the place over there. You have plateaus over there. You have stationary points like over there, which are not like local minimums. So you have all of things, many things that can happen. And if you initialize this like not in the correct way, you're going to end up really nowhere. Okay, so this is what we have to deal with. All right, so what are the classical algorithms? So essentially, they are not so different from what you do in the convex case. Okay, so the convex case is a good test bed for designing algorithms. And this is still a finite sum. Simply H is much more complicated. And we're going to use still a HGD. Okay, this doesn't change, but you add some additional things. Okay, there is like mini batches. There is like momentum. Okay, but you add like some memory of the past iteration. Okay, so this is like used quite a lot. There's a nice review paper by Léon Bautou, and this is my book. You will see like more of it like in a few slides. And then there's also Adam. Okay, so Adam with its precursor Adagrad will do essentially reconditioning of the updates by dividing the gradient, okay, by some scaling factors, and those scaling factors act on each coordinate separately. Okay, so this has some good effect in practice. The problem is that like the global guarantees in the convex case are not really great. Okay, it does converge if you set the parameters correctly, but it does not really improve over gradient descent in terms of bounds. So it's still quite open. And if you're not convex, what you can only show is local guarantees. Okay, essentially, if you use HGD, you're going to end up on average in the stationary point. Okay, and so clearly, with the guarantee that we have from non-convex optimization, you can end up at many places. You can end up any of those like local minima. You can end up there, which we like. You can get stuck over there, but none of the guarantees from non-convex optimization can let you say anything concrete. So the question is, why does it work so well? Okay, so this is like something which is still a mystery to me. And what I will do is provide a very qualitative, simple analysis in the simplest possible nonlinear model. Clearly, there's still a lot more to do. All right, so let's like simplify the model even more. Let's take a one layer neural net. So this is my X is my input data. Those are my hidden neurons. Theta 1 will be my input neurons. Okay, so my input weight, sorry. So I multiply X by each of X. I multiply by a vector. Okay, and this is like all of those weights. And I do this like m times. I have m hidden neurons. And I'm going to assume the loss remains convex. So you see what I mean by convexity still needs to be there. At least it's sufficient for us a key question whether it is necessary or not, but at least it's sufficient for what I'm going to say. And what we're going to use is simply that the prediction function h is an average of terms, okay? And each of those terms are parameterized without any sharing of parameters, okay? So I'm going to assume that I put in Wj all, let's take one neuron, I put all the input weights and the single output weight together in Wj, and my function h is a sum of terms, okay? C of Wj, which is with no sharing of parameters. So this is crucial for the analysis, and you can think about it, but this will not be true if you have more than one hidden layer. If I take two hidden layers, you have sharing of parameters, so this is not true anymore, so our analysis does not apply. And what is the main insight, okay, which is a classical in that setup, is going to replace this finite average, okay, write it the integral over some measure, and the measure will be the empirical measure. So this is just rewriting at the moment, but the key will be to use mean field techniques common in math and in physics, where you're going to, when they get more and more neurons, okay, and if you zoom out a bit, those neurons will have a density, okay, so we're going to replace the analysis with a finite amount of neurons by a continuous amount of neurons. So this is not a new idea, okay? And the key here is to use over-parameterization. If I only have a small number of neurons, I will be very far from having a density, okay? This is where the large M is important. And this dates back from various people, okay? Baron, other people, Nicolas Leroux again, you can say hi, and other people. So the key here is to have a large number of neurons, and the key here is going to convexify the problem. Why? Because now I had a weird non-convex, nonlinear function. But now if mu is my, okay, I don't know why. And if mu is not your parameter, now your prediction function h is linear and mu. Okay, so linear and mu, R is convex, you're back to a convex problem. Okay, the catch here, of course, is that it's convex, but in a space of measures. Okay, so you have to optimize over the space of all measures. First, you're supposed to optimize over the space of all atomic measures with m atoms. Let's ignore this one, but then this is a high-dimensional space. Okay, infinite-dimensional. We could use Frank-Wolf techniques. We have experts in the room. Okay, but the problem is that in those techniques you have to add neurons one after the other. And the task of adding one neuron is not so easier than solving the whole thing from scratch. Okay, so I'm not going to talk about it. And what people do in that setup is to use gradient descent. Okay, so I've mentioned it earlier. They use LGD. Okay, but let's take a gradient descent, which is simply, it's called like backpropagation. It's simply ignoring all of what I've said and still do gradient descent. Okay, so there are three questions that are relevant to me. Is when m goes to infinity, is there a limit for that algorithm? Does it make some sense to get m very large? If yes, does it go to global convergence? Okay, and if it converges globally, where? And can you say something about the minimizer? So I'm not going to focus on this one. You can look at the paper with Enaik by yourself. So the first question, so we're going to look like at gradient descent, and we're going to simplify the problem even more. Okay, so here, that part of the talk is really a sequence of, say, renunciation. Okay, so you're going to make more and more assumptions and get further and further away from the true thing. Okay, and here I went from many layers to one hidden layer. Now I'm going from descent to flow. Okay, so it's a gradient flow. So M here is just a way to make things like well normalized. And this is one idealization of HGD. Okay, so it's not the topic of today, but you can show that in the limit of vanishing step sizes, if you do a single pass of HGD, this will follow the gradient flow. Okay, so this is what we're going to leverage. Forget about this one. All right, and so the first thing is the limit when m goes to infinity. Okay, so here I'm going to give zero details, but that limit as a name is called a Wasserstein gradient flow. So Wasserstein is a distance over probability measures based on optimal transport. So once we have such a distance, we can define a gradient flow for that measure. And if you want to know more, nice book by Ambrosio and colleagues. And what you can show, okay, and what you being like a bunch of people, and I think the first one to notice it was Nitanda and Suzuki, and then we worked on it, and also Montanari and others work on it, is that when m goes to infinity, you're going to have a gradient flow of the measures of a neuron. That gradient flow will follow a partial differential equation, and that PDE will be exactly a transport equation. Okay, so many details which are like hidden, but at the end, this will allow us to get our results. So it has a limit, it has a name, okay, and does it converge? Okay, so here I'm going to give the informal theorem, which means to hide everything under the carpet. Okay, and what we show with René Chiza, who is now a professor at EPFL, is when the number of neurons goes to infinity, so I get more and more hidden neurons. So this is a mean field limit. I have m infinite, so I'm going to really look at the flow for the measure of neurons. Then the flow converges to the global optimum. Okay, so here the key is that the process is not you have many local minimum. Okay, you get many like paths where the flow will get stuck, but you can show that if you initialize correctly, you're going to convert to the global optimum. So again, just one hidden layer. Okay, so we cannot say anything if you have more than a hidden layer, even less if you have like transformers and things like this. This is a mean field limit. And we need two key ingredients. Okay, you cannot, for this to be true, you need to have some assumptions because there will be a lot of counterexamples otherwise. The first one is convexity of the loss. Okay, so if the loss is not convex, our results, we don't know if it holds, probably not. So two things. First, you need some form of homogeneity for the problem. And it turns out that the revival of neural networks partially comes with a new activation function. It used to be the sigmoid, which is non-homogeneous, and now people use a lot the called the ReLU, rectified linear unit, which is a positive part. So if you multiply u by a constant, you multiply the output by the same constant. Okay, so you need some form of homogeneity, which we do in practice, and you need above all to get a diverse set of neurons. Okay, you need, if you initialize all neurons at the same place, it won't work. You need to have a uniformity in some sense, and it turns out that this is what people do in practice. Put a big Gaussian over your neurons, and if you have that, then the assumptions of this informal theorem are met, and you get global convergence. So here, it's what I call a blessing of over-parameterization, positive part, but it's only qualitative. So here, I will not tell you how fast it converges to global optimum. I have no clue. And I won't tell you how big the number of neurons needs to be. Okay, so nothing quantitative, which is in stark contrast with what we had before. What we had for convex was very quantitative. Okay, rates zero quantitative, so there's still like some work to do. Like my big data experiment, okay, in 2D. Okay, so here I'm going to fit like neural networks in 2D. Okay, so this is like the shape of the neural network. This is the input weight, the ReLU, the output weight. I'm going to generate my data from 5 neurons. Okay, 5 neurons means like 5 directions in 2D, and in the plots I will plot those 5 directions in dotted, and the neurons will be plotted. Okay, and if you get a perfect model, if you recover the 5 neurons. Okay, so in the plot I'm showing here, you're going to start from small values, and they will evolve. So in blue you see the particles, which are the neurons moving. And so we generate the data with 5 neurons with no noise. So this means that if I use 5 neurons, I am able to perfectly converge. Okay, so if I had no local minima, then I will always converge. And in some situations, which are quite common, if you have just the correct number of neurons, you will not converge. Some neurons are well estimated, but some are missing. Okay, so this is well known. Neural network training gets trapped into local minimum. Okay, those have not disappeared with deep learning. Okay, and what our research suggests is that if you take a lot of neurons, okay, then the flow, all neurons will end up converging to the correct ones. Okay, so this is what our result is suggesting. Open problem, when m is a bit smaller, it still works. Okay, it converges very robustly to the good set of neurons, but this is still like quite an open problem even in 2D. I have a small video just to highlight the fact that the dynamics are really like not like convex optimization. Right, so you see the neurons, they move and they move along, okay, and they end up converging, okay. So let's once more. So it's a video by Lena Shiza, okay. I'm clearly not able to do that, and just to highlight the fact that even in that simple setup, the dynamics are really bizarre. There's a lot of interactions among the various neurons that nobody knows how to distinguish. All right, so to summarize soon, first, I've mentioned that over parametrization is a blessing, but it could be a problem for generalization. So there is common wisdom, okay, that you see a lot everywhere, that models do not generalize well with too many parameters. Okay, so if you remember a single thing from the talk, will be that this is not really true. Okay, what counts is not the number of parameters, but more some norm of those parameters. Okay, there are many various norms that we characterize like performance on unseen data, but really it's not the number of parameters. Okay, so you should hopefully remove this from your common wisdom. And if you want to make this common wisdom like new and more up to date, this is a book for you. Okay, which you can buy, which is also like available on my webpage for free. Okay, so you look at it, you enjoy it, and then you buy it to allow me to buy a pair of skis or a new roadmap. So this is the common wisdom, okay? But there is something, and it's not true, but there is some truth to it. Okay, so if I have a neural network with many parameters, okay, typically it will have a large norm, and if I take any neural network that fits the data quite well, many of them will not generalize. Okay, but what you can show is that gradient descent, okay, as a way to regularize the output. Okay, it's often called the implicit bias or computational regularization. And there's a series of work by Surya Gunasekar, Soudry, Natis Rebro, which we also worked on, showing that if you do gradient descent, not only in that setup it's going to converge to a global optimum, okay, but if you have a perfect data fit, among all those fits, it will select the one with minimum norm. Okay, so those works have considered linear problems, so you get the Euclidean norm, and we have worked with NAIC on neural networks, but essentially the same phenomenon appears. You get to some implicit bias, so you don't end up in any solution, and it is still a subject of quite a lot of work. All right, so what are the current research directions? Okay, so here I'm going to make the next and my last two slides a list of current problems in optimization for machine learning. This is like done with jet lag, okay, done with my personal taste. So if you're not in it, don't worry, you're still like relevant for machine learning. Okay, so and probably I've forgotten like many of you. Okay, so the one which I see a lot first is part of step size. Okay, so some of my friends tell me I'm obsessed with step sizes. Okay, I used to be, not so much anymore. So I'm improving, but still this remains a big problem because the gamma, which I was showing, is still a pain. Okay, so you try an error. You want to have several of them. Okay, so Adam is doing this essentially, having several step sizes, and this remains like a key headache. Going distributed, this is still very active because clearly all of those models are not learned on a single machine. Okay, it's already a problem for convex, so imagine for not convex. And there are also like all the convex-like problems, which are not convex, but which are for which you have guarantees, the min-max, game theory, and so on. Okay, it's still quite active. But what I want to emphasize for the last slide is all the non-convex problems. Okay, so the first, which we have worked on as well with Lena Shiza and Edouard Yalon, is when you have a lot of neurons, how should you scale the problem? So for the expert in the room, I had a 1/m everywhere. Okay, so I had everywhere 1/m. Okay, that 1/m is not there randomly. Okay, it's there because it allows you to really optimize over the measure, and there is other ways of normalizing the problem. Okay, and in the paper with Lena and Edouard, we highlight the fact that if you don't initialize correctly, okay, you're going to fit correctly, but there will not be any form of feature learning. This is what you call the lazy regime, okay, and this is indeed what is called the neural tangent kernel, okay. So this is highlighting the fact that when you have more and more neurons, you have to be careful in the way you initialize and scale things, okay. There is a nice extension to deep networks by Yang and Yu, the so-called MuP parametrization. Then going beyond like one hidden layer, okay, going closer to the real game, I have to say that there are a few results on ResNet, particularly by Pierre Marion, but transformers are still far away from having such direct theories. I think Claire has some work on the simplified version of transformers. If you go to Mamba, it's even worse. And the key here is that I don't expect that we're going to be as quantitative as we are for convex. Okay, I think this is hopeless. But trying to get what makes optimization work in the setup, this remains to be a key open problem. And the idea is understanding a piece of it would allow us to get some improvements. Then getting quantitative again. Okay, so here in fact we go back to convex, but not yet. So there is a nice series of recent work called like scaling laws. Okay, I think the word is very cool, showing that essentially I have a neural network which is very big, transformers, LLM, whatever you want, and you want to know somewhat in advance or as you go along how much, what is the performance as a function of number of observations, compute, mini batch, number of neurons, and so on. Okay, so they build those like empirical scaling laws. One key question is how do you get them using a bit of math and assumptions? Okay, so this is like you can ask like the packets were over there more about it. And what I'm going to talk about on Thursday is one instance of this. Okay, so here again we simplify the problem a lot. Forget about neural networks, go back to convex. Okay, forget about AGD, go back to GD. Forget about the loss, go back to quadratic, and now we can start to do things, okay? And what we show with Frédéric Kutzner is that the problems will come up with because the data which you learn on, typically in text, have a very typical behavior which is not classical. It's called the Zipf law, where the frequency of the kth most frequent word goes down to 0 as 1 over k, and this is like very common in many natural phenomena, and this will make the problem really hard to optimize. And if you want to know more, you can look and come on Thursday morning. And finally, what I've not been able to answer, and this is something which I think few people still work on, is what makes a problem easy to optimize. Okay, so we know that one layer, many neurons, it's fine. We know that if you're deep enough, it's going to be fine, but it's just empirical. Nobody, I don't know of anybody with a good argument to say that a deep net will always fit the data. Okay, it's true empirically, but nobody knows what this means, how you can prove it. So clearly, convexity is sufficient. I've shown like that is you can get to nice bounds, but is it necessary? I do believe that you will need still be to have some form of convexity, either at the loss level or some linearity at the predictor level. But at the end, this is still very open, and the idea, if you want to go closer to convex bounds, there is still a lot of work to do. And on this, thank you for your attention.
Yeah, thank you for the beautiful talk. I think we have plenty of time for questions. Who wants to break the ice?
I have. Can you hear me?
Yes.
Yeah.
I actually have two questions. The first one is about like the common wisdom like for the generalization properties. Okay, so like common wisdom, I think like it's guided from let's say statistical convergence rate from some measures like Rossi dimension or like market complexity. And in your experience, how do they reconcile with the optimization point of view?
I think one bound, which is the most classical one in statistics that you learn in class 1, if you do least squares with d dimensions and n observations, the rate is sigma squared d over n. Okay, this is what you learn in any given class. So it makes you believe that, oh, d over n, so n has to be larger than d. And if n is of the order of d, problems. This is for ordinary least squares. This is for least squares with no form of regularization. Okay, so as soon as you add a bit of regularization, either explicitly by penalizing the norm, or implicitly using gradient descent, then you're away from that number of parameter business. And same thing in VC dimension is also for the empirical risk minimizer. Regularize, you always regularize one way or the other, so you avoid that d over n business. So I think there's no incompatibility with optimization. Simply, you need to regularize a bit, okay? And this is one way of doing it is by GD.
Like, how do you find your work extending to let's say structured data domains like graphs?
Which the convex one I don't know, and non-convex I don't know if people have tried, but as soon as there is some form of over parameterization that leads you to like a continuum of neurons, you could imagine doing it. I don't know if people have tried, but you could imagine like if you have like if you have a graph and if you do average over like your neighbors, you could have some mean field effect, but I don't know the specifics.
Yeah. So Russell has a question. We're going to pass around this beautiful microphone.
Thanks also for the lovely talk. To your last question about what makes a problem easy to optimize, what I think about is when we were focused on compressed sensing. And there, you had these non-convex problems and you add a restricted isometry property. And then that basically says that you have no stationary points other than global minima. I mean, do you imagine some similar, possibly unverifiable assumption like that being able to be formulated for machine learning?
Yeah, I think that's a very, very good point. So I think, in fact, for that setup, for that simulation, key here is that the directions were somewhat well spread. Okay, so I can easily give you neural networks in 1D with 5 neurons, which you can't fit. Okay, without like a lot of neurons. Okay, so the randomness of the problem is important. But the issue that I see with compressed sensing is that, sure, this was okay because in the signal processing, because you could choose the features. But for machine learning side, that assumption is not verifiable and never true. Okay, so because you take two nearby features will make those assumptions like not true. So I agree that if you want to show a thing, you need to assume some form of randomness, typical case. And I think this is a nice area for research where you replace worst case performance by average case performance. So average over a class which is large enough so that the hard cases have zero mass. Okay, it's classical in smooth analysis. And this is, to me, a nice way of moving forward, but doing it in practice for those nonlinear models remains difficult. I don't know of any people being able to do that, but clearly I agree, some form of like randomness should help. I don't have my glasses, so it's going to be difficult. But that's easy. I can't read them, but I'm sorry. Merci, Claire.
Regarding the optimal transport approach to understand the convergence of neural networks, are you aware of any approaches that try to understand transfer learning, fine-tuning as constraint optimization over measure spaces?
Thank you, Claire. No. Yeah, so sorry for all the effort, but thanks for the No, I think that's those are good questions, but no, I don't know.
Thank you for the talk. You mentioned mean field parameterizations. So I have sort of an open-ended question. What's the best part of it, and what's the worst part about the mean field approximation? And because there's also these, standard parameterizations in neural networks. They seem to work okay. And
would it be standard like?
Unfortunately, it's called the standard parameterization. Yeah, you initialize the weights in a different way than the mean field.
No. Okay. Yeah, so I think the good thing about mean field is that so if you like PDEs, it gives you a PDE. If you like optimal transport, it gives optimal transport. And I think to me, it's a good way to revive optimal transport folks in Paris. Okay, so there are many of them. So the math part is a bit different, but I do think that the feature learning part is important. Okay, so let's say let's say you have your problem, let's say variable selection. You have like a bunch of data, a lot of irrelevant features. If you want to learn the correct directions, you need some form of feature learning. And mean field will give it to you. All the others will not give them to you. It will work a bit, but take the classical, like I think I forgot the name, Glorio initialization is not even as the correct factor. And it works well if the number of neurons is like 100, but if you blow it up, it will always fit because it does converge to like a kernel method, but you won't do the feature learning that people care about. So this is for the positive part. For the negative part is that it's hard to prove anything. Okay, so the only thing you can show, in fact, this is how we leverage optimal transport, is if you start to get on the flow with a measure with a density, you have a density all the way through. It's a theorem for multiple transport. And, but apart from that, it's very hard to say anything more. And in fact, since you're going to converge to a singular measure, this is where our mathematician colleagues are a bit like a bit clueless on how you analyze dynamics that end up in a singular measure and how you make this like quantitative. I've asked many of my colleagues, and they always come up by interesting, but nothing more. Yeah, so the bad part is it's hard to analyze. It's already hard with one hidden layer. It's even harder if you go like with more layers. But I do think that the feature learning capabilities are really obtained using the good scaling.
Hi, thanks for the nice talk. You're talking about feature learning. And one thing I have a problem with the feature learning idea is that it's not super well defined. You can find different ideas of what feature learning means. Typically, people ask that like the activations are stable as you're scaling the width. They don't go to 0 or blow up. And that the change in the activations is stable during training. Is this what you mean by feature learning? Or how do you feel about this situation?
I agree that things are often ill-defined, but the example I gave, which is I want to learn the subspace which is required for predictions. It's well defined. Do you find it or not? Are your neurons aligning with that subspace? Yes, no. This can be quantified. It's only possible for linear subspaces. Okay. If you go beyond, if you want to learn like smooth functions, then it's a bit harder. But I agree with you. You have to define it properly. And beyond the linear case, it's unclear.
Okay, looks like everybody's questions have been answered. Before we wrap things up, there's going to be 2 more talks by Francis Bach tomorrow at 11:30 and on Thursday at 11:30. You can also attend even if you're not registered for the optimization and learning workshop. Okay, just so that you know. And so on that note, let's thank the speaker again, and let's move to the, there's a reception with wine and cheese, and it's probably not up to French standards, but it is wine. So let's thank the speaker again, and